So in this video we are going to discuss about unijunction transistor. In short form it is represented as UJT. So it has three terminals, namely emitter and base. Okay, base 1 and base 2. So you have three terminals. Okay, so this is your symbol for UJT. This is your symbol, and inside this one you have a P and N junction. Okay, so you have only one junction. Okay, so this represents a junction, so it is named as unijunction transistor. Okay, so this I can redraw it as, or the equivalent circuit of this one is PN junction. I can draw it as a diode, and this area I can draw it as a resistance. Okay, so this RBB is equal to RB1 plus RB2, and if I apply a voltage divider bias for this value, I will get VA is equal to total voltage into the resistance across this one, VI, divided by total resistance, RB1 plus RB2. So this whole term I can write it as intrinsic standoff ratio. Okay, so what is intrinsic standoff ratio? RB1 by RBB, right, where RBB is nothing but RB1 plus RB2. So the value of intrinsic resistance intrinsic standoff ratio will ranges from 0.56 to 0.75. So first we are going to apply positive voltage to this one, VE. Okay, so if I apply a forward bias, that is since it is P and N, this is P and this is N, so you have to, forward bias means you have to apply a positive supply to VA. Okay, so initially you can see, okay, so since the VA is equal to VBB, intrinsic standoff ratio into VBB, this value is always higher compared to this one if V is 0. Okay, so if so suddenly I am not going to increase the positive value. Slowly I am going to increase the positive value. So initially, if I apply a positive value to VE, since the VE is initially it is less than VA. Okay, so that supply voltage, that voltage is not enough to turn on this UJT. Okay, so when it will turn on the UJT means you have to apply a voltage called VP. Okay, so once since I am going to increase this more and more positive, okay, only when VE is greater than VI, it is going to be positive. Okay, so now if I assume that VE is greater than VI, so now this UJT turns on because of the diode is now it is forward bias. Okay, so the more number of holes, okay, the more number of holes will be injected into this N region. Okay, this N region. Okay, but since we are applying VBB supply, positive supply to this is positive and this is negative, right? This is positive and this is negative, and the holes is also positive. Due to this electric field, this holes is attracted towards B1. Okay, this holes is attracted towards B1. Okay, so you can see as long as the V is below the Vp, it remains the diode remains in the reverse biased, and the no emitter current will flow, and therefore the UJT is off. When the value at which the diode starts to conduct is called as peak point voltage, that is Vp. Okay, so I can write this VE is equal to V gamma plus VA. Okay, V gamma plus VA. So VE is equal to V gamma plus VA. Okay, so what is VA? VA is equal to intrinsic standoff ratio into VBP. Okay, substituting 1 in 2. So once V is equal to Vp, the UJT starts to conduct. Okay, then the excess hole gets inducted into the base region and are swept by the electric field towards the base terminal B1. This presence of excess holes, okay, this presence of this excess hole will definitely reduce the value of this resistance, right? This excess hole will reduce the value of resistance, thereby the more current will flow. Okay, more current will flow in this direction. So the current is increasing, resistance is decreasing, thereby the voltage also decreasing. So this region is called as a negative resistance region. Okay, so the presence of excess hole slightly reduces the resistance RB1, which in turn reduces the intrinsic standoff ratio. So this action is called as a conductivity modulation. Since more holes are injected into this base region, this will reduces the RB1 and intrinsic standoff ratio. Therefore, because VA is also reducing, right? So the IE start increasing. Okay, so IE start increasing and VE start reducing. Okay, so this region, this will produce a negative resistance region in the VA characteristics of the UJT. Okay, you can see till this one it is in cutoff. Okay, whenever the VE equal to VP, V is equal to VP, the UJT turns on. So till this one UJT is on. Okay, so once it gets on, and if the VE start to increasing, the more and more whole current, more and more emitter currents will flow. If I increase the emitter current, the resistance get decreased, thereby the VE also get decreased. Okay, so this region is called as a negative resistance region. Okay, and we can't able to further increase the VV once the IE reaches the point called IV. Okay, after that the VE remains constant. Okay, so this region is called as a cutoff region. So this is a working about the working of UJT. Let's see how this is used as a oscillator. Okay, this is also called as a relaxation oscillator. Okay, so in the UJT I am going to connect RE and CE value. So you can see initially the current will flow like this. Okay, so initially the capacitance, there is no voltage across this capacitance. Okay, so once if it is charging in this direction, okay, I can write V is equal to the since the capacitance is charging, I can write VBB into 1 minus e power minus t divided by RECE plus V gamma, because you have to turn on this UJT, right? So I am going to equate this equation with respect to this fourth equation with respect to this fifth equation. I am going to equate the 4 and 5. If I equate 4 and 5, equating equation 4 and 5, I'll get this, and V gamma get cancelled out, and I can write and VBB also get cancelled out, right? VBB also get cancelled out. So I can write 1 minus intrinsic standoff ratio is equal to e power minus t divided by REC. So if I take taking ln on both sides, okay, taking ln on both sides, I will get ln of 1 minus equal to minus t divided by REC. Okay. So this I can write it as t is equal to RECE ln 1 divided by 1 minus intrinsic standoff ratio. Since t and f is inversely proportional, that is f is equal to 1 divided by t, I can write frequency is equal to 1 divided by RECE ln 1 divided by 1 minus intrinsic standoff ratio. Okay. So you can see initially the capacitance get charged, right? So if we like this only, the capacitance will charge. Okay, in this direction only the capacitor will get charged. Okay, so if the capacitance get charged, and once if it reaches the value, the UJT get turns on, right? So only from here only UJT is on. Okay, if UJT is turned on means once this value is enough to turn on this UJT means once it reaches the VP, I told you the V start to decrease, right? So this will start to discharge in this direction. Okay, it start to discharge in this direction. So the capacitance discharging will look like this only. Okay, it will start to discharge here. So and the remaining cycle will repeat. Okay, so you can see since here only the UJT is turned on, and I already told you that VB1. Okay, so the VB1 is 0 till the transistor get turned on. Once the transistor get turned on means this is similar to the waveform of this one above equation V. Okay, so the inverse of this one is across the voltage across the VB2. Okay, so let us discuss one problem on UJT relaxation oscillator. Design a UJT relaxation oscillator in order to generate a sawtooth waveform at a frequency of 500 Hz, and they have given VBB is equal to 20, VP is equal to 2.9 volt, VV is equal to 1.118 volt, IP is equal to 1.6 milliamps, and IV is equal to 3.5 milliamps. You know the formula for frequency, that is equal to 1 divided by 2.303 RECE. Instead of ln I have replaced by log, that is why I have multiplied with 2.303 log 1 divided by 1 minus intrinsic standoff ratio. So I am taking the intrinsic standoff ratio is equal to 0.56, and I know that VBB is equal to if the I can write it as IPRE plus VP. Okay, this value is VP now. Of the current is flowing as IP means. Okay, if it is IV means this I can take it as VV. Okay, so if I equate this one, I will get VBB minus VP divided by IP. Okay, that is greater than RE. Okay, so if I substitute VB minus VV divided by IV, that value is lesser than RE. So I can write RE is the range of RE from the above derivation. Okay, so once if I solve this equation, I will get RE values between this only between this value. So I can take RE value as 10K. So if I take RE as 10K, so I know the value of intrinsic standoff ratio, F and R. So only I have to find the value of CE. So once if I find the value of CE, I can substitute here. Right? So RE I know, CE I know. So from this one I can design a relaxation oscillator. So the application of the UJT is it is used to generate a sawtooth waveform generator, and it is used as a timing circuit, and it is used to generate a non-sinusoidal oscillator. It is not a sine wave, right? And it is also used for the triggering device for SCR, silicon control rectifier, and triac. Thank you.